One of Gauss' proudest achievements was the quadratic reciprocity. He called it his golden theorem. Gauss attempted 10 different proofs of quadratic reciprocity, each of them generalizing in a different direction. The reason is because quadratic reciprocity encompasses many deep ideas. In this video, we're gonna get a glimpse of some of these ideas via Artin's generalization. Okay, so what is quadratic reciprocity? Well, given odd primes P and Q, let us define the Legendre symbol of Q over P to be 1 if Q is a square modulo P and minus 1 otherwise. Then the law of quadratic reciprocity says that Q is a square modulo P if and only if P star is a square modulo Q, where P star here was defined to be P if P is congruent to 1 mod 4 and minus P if P is congruent to 3 mod 4. In other words, P star is always going to be congruent to 1 mod 4. Now, how can we derive this from Artin reciprocity? The key there is to realize that the Artin map is actually a generalization of the Legendre symbol. To see that, let us consider the case of the quadratic extension Q adjoint square root of D over Q, where D here is square free. Then we claim that the modulus given by 4 times the absolute value of D times the infinite prime is an admissible modulus for this extension. The reason is that the finite part of the conductor of this extension must always divide its discriminant. Now we know the discriminant of a quadratic number field. In particular, we know that it must divide 4 times the absolute value of D. Thus, the conductor of L over K must divide 4 times the absolute value of D times the infinite prime. In other words, this modulus M must be an admissible modulus. So, given that admissible modulus M, let us figure out what the Artin map is in this case. First, observe that we can think of this fractional ideal group as the free abelian group generated by primes Q that do not divide 4 times absolute value of D. The Artin map then sends every such Q to the Frobenius Q element of the Galois group. So what is this Frobenius Q element? Well, let's say that beta is a prime lying above Q in OL. Then OL over beta is a finite extension of Z mod QZ. So we have a finite extension of finite fields. Now, every such extension is Galois, with Galois group being generated by the Qth power map. Recall that this was called the Frobenius Q map for this finite extension. One can show that if Q is unramified in OL, then we can lift this map to OL, and then even to a map on L over K. In the case when L over K is abelian, this gives a well-defined element of the Galois group of L over K, independent of the choice of the prime beta lying above Q. Now, in the case when L over K is Q adjoint square root of D over Q, we claim that the Frobenius Q map is the identity if and only if D is a square modulo Q, i.e. if and only if the Legendre symbol of D over Q is equal to 1. Now, we can rephrase this statement even more if we identify this Galois group with plus or minus 1. Here the identity corresponds to 1, and the map that sends square root of D to minus square root of D will correspond to minus 1. Then under this identification, this statement becomes Frobenius of Q is 1 if and only if the Jacobi symbol of D over Q is 1. In other words, the Artin map is just a generalization of the Jacobi symbol. So now, let us see why the Frobenius element corresponding to Q is identity if and only if D is a square modulo Q. Let us explore what it means for this Frobenius Q Map to be the identity. To this end, let us revisit the definition of this Frobenius Q Map. Recall that it was defined as a lift of the Q power map on the field OL mod beta, where beta is any prime lying above Q. Now, from Galois theory of finite field, we know that the Galois group of this extension is cyclic, generated by the Frobenius Q element. So this Frobenius Q is identity if and only if this Galois group has size 1. This would mean that this extension must be trivial, i.e. Q splits completely in OL. Now, from the theory of decomposition of prime ideals in the Dedekind domain, we know that this happens if and only if D is congruent to a square modulo Q. The reason is because we can always show that this quotient OL over QOL is going to be isomorphic to Zx quotient L by x squared minus D. Now, if Q splits completely in OL, then by Chinese remainder theorem, we have that this quotient here is going to be isomorphic to FQ times FQ. In particular, this quotient is not a field, so x squared minus D cannot be irreducible, and thus x squared minus D must split completely modulo Q, i.e. D must be congruent to a square modulo Q. Conversely, if D is congruent to a square modulo Q, then we see that x squared minus D splits completely in FQX, and therefore this quotient is isomorphic to a product of FQ. In particular, it is not a field, therefore Q cannot remain a prime ideal in OL. This implies that Q must split completely in OL. Thus we have that the Frobenius Q map is identity if and only if this Galois group is trivial, i.e. if and only if this extension here is trivial. This is equivalent to saying that Q splits completely in OL, which holds if and only if D is congruent to a square modulo Q. Thus we have established that Frobenius Q is equal to 1 if and only if D is a square modulo Q. And thus the Artin symbol can be identified with the Legendre symbol. Now, let us go back to quadratic reciprocity. From our previous discussion, we see that the Legendre symbol with P star here could be viewed as the Artin map for the extension Q adjoins square root of P star. Note that since P star is congruent to 1 modulo 4, an admissible modulus for this extension is P infinity. Because since P star is congruent to 1 modulo 4, we know that the discriminant of this quadratic extension must be P star. Thus, the finite part of the conductor of this extension must be P. Therefore, P times the infinite prime must be an admissible modulus. Now, Artin reciprocity said that this Artin map must be surjective and its kernel must contain Pm. Thus, we have a surjective map from this generalized ideal class group to plus or minus 1. Now, in our video on generalized ideal class group, we have shown that this generalized ideal class group must be isomorphic to Z mod PZ star. Thus, we get a surjection from Z mod PZ star to Z mod 2Z. But there is only one such possible map, namely this Legendre symbol. So why is that? Well, that's because the kernel of this Artin map here must be an index 2 subgroup in Z mod PZ star. But Z mod PZ star is cyclic, so it has a unique subgroup of index 2, namely the squares in Z mod PZ star. Thus, this must be the kernel of the Artin map. In other words, this Artin map sends every square to 1 and every non-square to minus 1. so it is exactly equal to this Legendre symbol. And thus, we have proven quadratic reciprocity.